Now that we have seen the Kalman filter, its equations, and the overview with the flow chart, we can look at some of the properties that we want to discuss, which are very important for the filter from 2 points of view. One, whether it works appropriately as expected. Second, to build the tools to obtain more general filters than the Kalman filter. So, the properties of the innovations, that will be the first thing to look at, and the likelihood function for the system model. Likelihood function for the system model is going to be the major tool in what's called multiple model estimation algorithms, which will answer the question, which is our model? Therefore, we'll have an adaptive scheme that can estimate not only the state, but also estimate within some limitations, which is the model that the state evolves according to. So, the first thing is the innovations. We'll show that innovations constitute a zero-mean white sequence. The innovations are orthogonal to each other. E nu k nu j transpose is sk delta kj. That's the Kronecker delta function, which means if k equal to j, they are uncorrelated, they are white. This, under the Gaussian assumption, the uncorrelatedness implies also independence, and therefore the innovation sequence is strictly white. Without the Gaussian assumption, the innovation sequence is just white sense white. So what innovation sequence we can say it is? It's zero mean, and the zero mean property follows directly from the definition of what innovation is, the difference between the measurement and its mean. Therefore, the result should be zero mean. And we'll skip the proof of the whiteness. It's in the textbook. We just want to make an important comment that some people managed to publish papers ignoring this, and they were proven wrong. The state estimation errors are not white. Innovations are, but not the state. Okay, the next thing would be the likelihood function of a system model. If we consider the PDF of the measurements up to time k, that's z super k, or the zj's, j from 1 to k. This joint PDF, p of z super k, can be written down as p of the last element of this sequence, and here's the previous k minus 1 elements. Because this is a PDF of two random variables, each might be a large vector perhaps, can be written as the PDF of the first given the second times the PDF of the second based on the standard definition of the conditional probability density. Now, what is the first one? pzk given z super k minus 1. Now, the second term we can obtain by decomposing pz super k minus 1 in the same fashion all the way down to the conditioning being z0, the initial, the prior information. So what we have here is a product of the conditional PDF of the measurement at time I given all the previous measurements, and this product over all the i's. Now, if these are Gaussian, then pz at time I given z cap z super I minus 1 would be a Gaussian, because all the innovations are Gaussian, all the operations we've done are Gaussian, including the filter, and therefore every error now will be Gaussian. So this is Gaussian. Argument zi, mean is z hat I given I minus 1. Covariance is S of I, which can be written by using the property of the Gaussian, that this is really a quadratic form argument minus mean quadratic form with respect to S inverse, we move the mean into the argument. So it's Gaussian with argument Zi minus Z hat I given I minus 1, mean 0 and covariance Si. But what is this difference? This is the innovation. So this is Gaussian with argument innovation, mean 0 and covariance Si, which is the PDF of the innovation under the Gaussian assumption. Therefore, the joint PDF of all the measurements is the product of the PDFs of all the innovations. This shows, on one hand, an informational equivalence of the measurements and innovations. On the other hand, it is an excellent evaluation tool, very convenient, because it's much easier to write this as the PDF of the innovations. Now, but what did we really write here? We wrote a joint PDF of the set of available measurements conditioned on the system model itself, not indicated explicitly. But if you look at what we have here, this Z hat I minus 1 comes out from a filter. Si comes out from a filter. That filter is based on the model, dynamic model, measurement model, and noise model. So we have implicitly here the PDF of the measurements conditioned on the model, even though it is not shown explicitly. But this is nothing but the likelihood function of the system model. So the product of the innovation PDFs will be really the likelihood function of the model based on which those innovations were computed through the filter we are running on the system. What this can be used for is later in chapter 11 to evaluate the goodness of models, the likelihood of models in multiple model adaptive filtering, and this will be a major advance over the Kalman filter, which relies on a single model. We are already building the tools to be able to evaluate in real time various models, and what we need is an architecture of such model conditioned or model based filters which can solve the multiple model problem, and we'll see this in due course. Now, to summarize the Kalman filter, what we have is a minimum mean square error state estimation model consisting of the following. The initial state is unknown, assumed to be a random variable with a certain mean, that's the initial estimate, and the covariance, which measures the accuracy of the initial estimate. We have a model for the evolution of the system's state, might be a time-varying linear differential equation, or difference equation rather, in discrete time. That's the Planck equation or dynamics, driven by a known input, which is control or platform motion, and an additive random disturbance. This is the unknown part of the evolution of the state, the process noise, modeled as zero mean white, really uncorrelated or white sense white, stochastic process with a known and possibly time-varying covariance. The measurements are modeled as a linear function of the state with an additive random disturbance, the measurement noise, which is again zero mean white with known and possibly time-varying covariance. And the important requirement that all the random variables of the problem, initial state, process noises, measurement noises, are Gaussian and mutually independent. Then the minimum mean square error estimate, the optimum for the system under consideration, which is the conditional mean of the state given the measurements, follows from the algorithm we just saw, the discrete time Kalman filter. This filter computes recursively the minimum mean square error estimate of the state of a dynamic system through the following stages. Starting from the current updated state estimate, which is the estimate of the current state given the observations up to and including the current time, a prediction is calculated one step ahead for the next sampling time. With the predicted state, we can now calculate the predicted measurement at that time. And when the actual new measurement is obtained, the difference between it and the predicted value of the measurement is the innovation or residual, is what we calculate. Then the updated state at the next time will be obtained as the sum of the predicted state and the correction term. And the correction term is the product of the filter gain, which you obtain separately from covariance calculations, and the innovation, or the residual. And the covariance and filter gain calculations are done starting from the current updated state covariance. We obtain the state prediction covariance, so one step ahead prediction covariance for the state. With this state prediction covariance, we evaluate a measurement prediction covariance, which is, as we have shown, the same as the innovation covariance. And the filter gain is calculated from the state and the measurement prediction covariances is more or less, in a scalar terminology, the ratio of the state prediction to the measurement prediction covariances. The updated state covariance is then computed by taking the predicted state covariance and subtracting from it what we gained in terms of information from the new measurement. If we combine the covariance prediction and update equations together, we end up with what's called the discrete time matrix Riccati equation. For a time invariant system, if it is observable, the state estimation covariance will be finite, and the Riccati equation will converge to a steady state solution if, in addition to it, the process noise excites each state component as a second controllability condition on the f and square root of the process noise covariance, then the steady state covariance will be both positive, definite, and unique. And the gain of the filter reflects the relative accuracy of the predicted state versus the new measurement. If the new measurement is, quote, more accurate, unquote, than the predicted state, the filter gain will be high. If the predicted state is more accurate than the new measurement, the gain will be low. Now, if the state covariance matrix is positive semi-definite as opposed to positive definite, in the positive semi-definite, it can have one or more zero eigenvalues. This reflects the filter's belief that it has perfectly accurate zero variance estimates for one or more state components or linear combination of them. And this is an undesirable feature because it ignores the fact that all our models are really approximations of the real world. The innovation sequence in a Kalman filter is zero mean white or uncorrelated with covariance equal to the measurement prediction covariance. Now, the joint probability density function of the sequence of measurements is really the likelihood of the function model and is given by the product of the PDFs of the innovations, which are Gaussian under the linear Gaussian assumption. And again, in the real world, if they are not Gaussian, we will still use a Gaussian approximation in the context of Kalman filtering that will be generalized to multiple model filtering later. Now, if the random variables in the state estimation problem for a linear system are not Gaussian and all we have is their first two moments, means and covariances, the same Kalman filter algorithm is the best linear estimator, the linear minimum mean square error estimator, and the covariances are really the corresponding mean square error matrices. Even though they are called covariances, they are really mean square matrices because they are evaluated not about a mean, but about an estimate which is not exactly the mean. In this case, the Likert function, which is needed in an adaptive multiple model estimation, is still assumed to be Gaussian, because we have to acknowledge we don't know much better, even though this is clearly an approximation, and it has been shown to be still successful in numerous real-world applications. We can summarize in this remark, in a nutshell, what the Kalman filter does. It estimates and predicts the state of a linear system with zero mean white noise disturbances, both in the input and output. It reduces the uncertainties due to such white noises. Again, this seems very restrictive, but through a number of extensions, this technique has been used successfully in numerous problems where the disturbance do not satisfy these conditions. But they have to be well understood how the actual disturbances should be modeled such that A, they are close enough to the real thing, B, they allow us to use our solutions. So the essence of the extensions is to map the problem at hand into one that meets or nearly meets these constraints. Let's look at an example now. We'll take a system with a state x, two-dimensional vector consisting of psi and psi dot. This is a one-dimensional motion with position and velocity along the axis, which evolves according to this matrix or state equation. Xk plus 1 is 1t, 0, 1x, plus this v is multiplied by t squared over 2 and t. This is an initial condition, initial position 0, initial velocity 10. This is one-dimensional motion, and you can see by checking in discrete time that two eigenvalues here are 1. That's a double integrator. It integrates velocity into position, and the meaning of Vk is really acceleration. It integrates acceleration into velocity. And we'll assume the sampling interval for this illustration equal to unity. So this is our general form. Xk plus 1 is fxk plus gamma vk. So we have the second form where vk is really multiplied by a gain. V is a scalar, x is a two-dimensional vector, so gamma is a two-dimensional vector. And we will model the process noise as zero mean white with variance q. And the measurements will be the state position only, corrupted by additive noise, which means the measurement matrix is 1, 0, picks up only the first element of x, but in the presence of additive noise, and we'll run it for 100 sampling times. And we'll assume the measurement noise to have unity variance, and we'll leave open the process noise for the parameter that will illustrate its impact on the results. The two noise sequences will be mutually independent. Initialization, in this case, is done according to what we'll see a little bit later, two-point differencing procedure. Section 5.5 will cover this soon. We take the first two measurements and use them to estimate the initial state. You need two measurements which are scalar to initialize the filter because we have a two-dimensional state vector. And there is also another subsection, 5.3.3, which describes the Dynaist companion software to the textbook, how to set up a simulation scenario and how to design an estimator. The results that were shown have been obtained with Dynaist. There is a step-by-step description in the book how to use it. Okay, what we are interested in this case about the Kalman filter is the following results. We'll plot from Dynamis present the plots of the true and estimated trajectories of the system in the state space. The state space is really the position velocity space, also called phase plane in all the control terminology. And we'll look at the variances of the predicted position, that's the 1-1 term of the 2x2 state covariance matrix, k given k minus 1, and the updated position, kk. So the same 1-1 component. Then we'll look at the 2-2 component of the one-step prediction covariance matrix and the updated covariance matrix. And we'll look at the filter gains. And this will be done for 3 cases for different values of the process noise variance Q. If Q equals 0, no process noise, really, variance 0, clearly the matrix F and the square root of Q is not a controllable pair, because what we have is no noise. There is no noise that excites the components. So what we have is the position gain goes to 0. It's expected. After a while, when you accumulated enough information, you don't want any more information. Velocity gain goes to 0. This is similar to what we have seen earlier in the estimation of the motion of a point with perfectly constant velocity. This amounts to exactly the same model, constant velocity motion, no acceleration, because Q equals 0, no process noise. Whatever initial velocity it has, it will maintain it. Here we have an example of state estimates in position versus time. The two and the estimated are pretty much overlapping in this case. It's just a scale of the picture. If you magnify it, you can end up with better distinction between, slight difference between the true position and the estimated position. In the velocity, you can see the difference. The 2 stays at 10. Here the position moves from 0 in 100 sampling times to exactly 1,000, because it's exactly constant velocity. You can see the constant velocity here. And the initial estimate of the velocity was not 10, because it was based on noisy observations, as we'll see later, but in a relatively small number of samples, it converges to the true value, and then it stays there. What are the error variances? There's a predicted variance and updated variance for the position. The predicted variance, first all go to 0 eventually. You get perfect information, no process noise, prediction variance and updated variance become the same. At the beginning, you don't have yet perfect information, so here's the prediction variance, how it goes down, and the updated variance. That's for position, very similarly for velocity. The filter gain for Q equal 1. If Q equal 1, what we have now is the filter gain in position. This starts with some initial value, goes to steady state in a very modest number of steps. So pretty rapid convergence to steady state. Now this is the case Q equal 1, which means that we have process noise. It is non-zero, and you can check that the pair F and square root of Q, or gamma Q, turns out to be completely controllable, which means this noise, which enters as acceleration into the velocity, modifies the velocity, continues, propagates into the position, so the noise really enters into each state, either directly or indirectly. And you can see that the velocity gained, again, in a small number of steps converges to a constant. And these are non-zero constants. The state estimates in position versus time and velocity versus time plots are easily seen to be slightly different than before. The true state is not moving at a constant velocity because the velocity changes with the noise, and you have here the true velocity starts at 10, goes up, down. The velocity in this case is really a winner process because the new velocity equals to the old velocity plus white noise. So it changes, it drifts, and the position moves according to that noisy velocity now. The error variances will also go to steady state. The predicted is around 3. The updated is around 0.775 now for the position. For the velocity, predicted is 2, updated is 1. Here are the units, meter square per second square. This is a meter square variance, is obviously the dimension of the square of the quantity it pertains to. And you can see now that there is a difference, significant difference, between the predicted and the updated values for those variances. If in the third case Q equal 9, this is a very strong process noise, we have the filter gains are now higher. As we said, if the past information, state prediction, is not very good compared to the measurement, here the measurement has variance 1 all the time. But now the value of past information is significantly degraded by the process noise, according to which the system evolves. So we are going to have a higher gain, both in position and in velocity, than in the case Q equal 1. The actual trajectory and the state estimates, interesting to see how the velocity, which starts close to 10, quickly goes away, actually becomes even negative, then again close to becomes positive. However, as it changes, the estimate of the velocity is capable of following it with some error. There will be always an error, but it does follow it because we have the right model. Here is the position trajectory. Again, the difference between the estimated one and the true one is very small at this scale. The error variances for position, the updated is just a tiny bit below 1, around 0.9. For the predicted is 9. It's dominated by the process noise. So the process noise dominates, in this case, the prediction. It's very high level noise. And for the velocity, again, you have predicted velocity and updated velocity variance.